Hi! In today's lecture, we're going to look at frost diagrams. We'll be briefly introduced as to how to construct frost diagrams, and we'll focus on the interpretation of these diagrams. Let's begin. So here are the takeaways of the frost diagram. Number one, the thermodynamically stable states are actually found lower in the diagram. So if we go back to the frost diagram of manganese, you can see here that you have the different curves in your frost diagram, and you can easily assess which is the most stable state, and that is Mn2+. So you have to be very careful when you are concluding when interpreting frost diagrams. So this is a frost diagram for an acidic solution of manganese species. So it will be different if you have a basic frost diagram or the frost diagram for manganese that is under basic conditions. Number two, the slope of the line joining any 2 points in a frost diagram is actually equal to the standard potential of the couple. So what do we mean by the couple? So if you have this Mn point here connected to the Mn2 plus point, this means you have the Mn2 plus couple. Or if you're gonna go back to your Latimer diagram, it will be the reduction of Mn2 plus to Mn. Recall that for Latimer diagrams, the Latimer diagram is arranged in terms of decreasing oxidation number. So you'll find Mn at the right portion of your Latimer diagram. So you have here that 0, 0 point and 2, negative 2.36 point. So the slope of this line is just equal to the reduction potential of Mn2 plus to Mn. I have here a cropped picture of the Latimer diagram for manganese in acidic solution, and this Mn2 plus to Mn reduction corresponds to negative 1.18. So if you will get the slope of this, you can see that it is in a downward direction, meaning that you have a negative slope. It should be equal to negative 1.18. And if you look at this Mn2 plus Mn3 plus couple, so you have 2 negative 2.36 and 3 negative 0.86. As you can see from the general direction of the line, it is upward. So you can say that the reduction is, or you can say that the standard reduction potential is positive. And if you will get the slope of this line, you will get a value equal to 1.5. The oxidizing agent in the couple with more positive slope, meaning with a more positive standard reduction potential, will tend to undergo reduction. The reducing agent of a couple with a less positive slope will tend to undergo oxidation. So you have here the couple. So when you say couple again, we're talking about two species that are adjacent to one another in the Latimer diagram and in the frost diagram. So this is an example of a line wherein the slope is less positive. So you can say that this one will tend to undergo oxidation. So this is your reducing agent, and it will be oxidized to form this one. And if you have a line with a more positive slope, such as this one, then this oxidizing agent will be reduced. So this oxidizing agent will be reduced to this species here. So here is a concrete example for the manganese frost diagram. So you can see that you have Mn3 plus to MnO2. So this is Mn3. So you have Mn3 plus to MnO2. So obviously this is in the plus 3 state. MnO2 is in the, so obviously this is in the plus 3 state, and then for MnO2, manganese is in the plus 4 state. You have here MnO4 3 minus, wherein your manganese is in the plus 5 oxidation state. You see here that this line here for the Mn3 plus MnO2 couple, the slope is positive, but it is not that high as compared to this one. So you can say that Mn3 plus will tend to undergo oxidation to form MnO2. On the other hand, your MnO2 MnO4 3 plus couple has a more positive slope, as you can see from this line here. So you can say that MnO4 3 minus will tend to undergo reduction, making MnO4 3 minus an oxidizing agent of the couple, and in this case, Mn3 plus acts as the reducing agent of the couple. A species in a Frost diagram is unstable with respect to disproportionation. We have discussed this earlier if its point lies above the line connecting to adjacent species, or if you have a convex curve. So if you're looking for substances which will undergo disproportionation or not, you need to consider 3 points in your Frost diagram. So these points must be connected to one another. So you have here a convex curve, and if you have something like this, you can say that this point at the center will undergo disproportionation. And that can be supported by the fact that the Gibbs free energy of the substance of the intermediate oxidation state has a higher value than the average of the two oxidation states here, as you can see from the line connecting these two species. And that means it is more favorable for this to undergo disproportionation. So again, if you have 1, 2, 3 points, so this pertains to 3 species of a given substance of different oxidation states, and then you connect a line from the third one to the first one, and if the second one or the middle one lies above, in terms of the y-axis, lies above this line created between points 3 and 1, then this substance will undergo disproportionation. The opposite is true if you have a concave curve. So, 2 species will tend to comproportionate. What do we mean by comproportionation? So, comproportionation is just the opposite of disproportionation. So, an example would be if you have silver 2 plus reacting with silver. So, same element of different oxidation states producing silver plus. So, you can see that it's just the opposite of your disproportionation reaction. And if you have a Frost diagram here, you can see again we have 1, 2, 3 points, and you need to connect point 1 and point 3, or substance 1 and substance 3. If the second point or the middle point lies lower compared to the line created by joining points 1 and 3, then substance 1 and substance 3 will comproportionate to form substance 2. Again, all of this is due to the Gibbs free energy favoring the formation of the intermediate oxidation state.